So before we move on, I want to take the opportunity to talk a little bit about the units of radioactivity and what it is that we're trying to measure. So the first thing that we'll measure about radioactivity is the activity. This is basically how radioactive is a substance. And it's a rate. So the standard unit in SI is called the becquerel. It is abbreviated with a capital B, a little q, and this is equal to 1 decay per second. Okay, so 1 of whatever type of radiation is going to happen per second for every becquerel. So if I had one atom that was going to decay once in 1 second, it would have a unit of 1 becquerel. Another more historical unit is called the Curie, named after Madame Curie, a brilliant Nobel Prize winning scientist. It is equal to 3.7 times 10 to the 10, so a whole bunch of becquerels, or 37 gigabecquerels. Now, we're often not actually very interested in how much radioactivity is happening. From a safety perspective, we're more concerned with how much of this we're actually absorbing. So we have defined these other units. So if you imagine there's something radioactive, it's shooting off radiation. Only some of this is hitting you, right? And you need to know how much is hitting you at any given point to know whether or not you are safe. So we have ways of measuring that, and we have units for those numbers, and they're called the absorbed dose. This has an SI unit called the Gray, capital GY, and this is equal to absorbing 1 joule of ionizing radiation for every kilogram of body mass. The bigger you are, the more you can absorb. So it's normalized or divided by your body mass. And then we have units called rad, and a rad is 0.01 gray, and therefore also has units of 0.01 joules per kilogram. And that's how we measure the absorbed dose. What's not happening with the absorbed dose, though, because it still doesn't give us a ton of information, is it doesn't take into account what kind of radiation we absorbed. Some of it is more toxic and deadly than others. So we introduce something called the equivalent dose. And the equivalent dose has its own units. They're sieverts. And basically, it's the same as a gray. It's how much energy per kilogram of radiation you're absorbing times this radiation factor. And this radiation factor is different for the different types of radiation that you're absorbing and takes into account how dangerous they are for you. And then we have something called the Roentgen equivalent man, or REMS. And this is equal to 0.01 sieverts. So now we can get a value that gives us some sense of how dangerous the radiation that we've been dosed with is. And when you are working in like a radio lab and like medicine and stuff like that, you usually have a badge or even sometimes a digital device now that's measuring your equivalent dose as time goes on to ensure that you are not absorbing too much radiation too quickly and affecting your health. It's also important to note that we're actually all absorbing radiation all the time. Most of this is in the form of our food. You might eat some radioactive potassium. Some form of that is radioactive. Some of the iodine and like iodized salt and stuff is radioactive. And that's perfectly fine. We've evolved to deal with that, and our bodies can correct for it. It's only when we start to absorb too much radiation outside of what the natural level of radioactivity we're going to absorb is that we really get sick, and our bodies can't handle that. So it's just important to know what your dosing is and to limit your exposure to it when you start to get too much radiation too quickly. The last thing I want to note for you guys is something called the effective dose. So often when we're doing like medicine with radiation and stuff, we're targeting only a specific part of the body. And in this case, what we wind up doing is multiplying the sievert by another fudge factor called the tissue factor. And this takes into account what type of radiation you got and what kind of tissue it went into. And this can be very important. Radioactive iodine getting into your thyroid is very, very, very dangerous for you. Gamma radiation going into like fat tissue is quite a bit less dangerous. You could handle quite a bit more of that. So we need this factor here to determine how dangerous it is, given that only a portion of you has been irradiated, and what your danger level is. We still have a REM that again is equivalent to this as 0.01 sieverts for the effective dose. And we actually work backwards with the effective dose as well. We try and figure out what is the minimum dose that is going to be effective at destroying a specific type of tissue, if we're looking to do that with, say, like cancer medications and stuff like that, radiation therapy. So the last thing I want to talk about with you guys is the idea of the half-life. So the half-life is the amount of time required for half of the mass of a radioactive sample to decay. So another way of saying that is that at the end of one half-life, half of the radioactive material will remain. The other half will have already decayed down to a stable nuclide. And it's also important to note that half-life also applies to activity. So we could say that you'd have half the mass or half the activity. So it could have mass units or it could have activity units in this case. And there is some interesting algebra to be done with half-lives, but we're actually going to keep this pretty simple. Just talking about, in our problems, just talking about whole values of half-lives. So let's look at an example of here. So an example problem might read something like, how much of a 28.3 gram sample of plutonium-241 will remain after 56 years if it has a half-life, which I'll abbreviate as T subscripted 1/2, equal to 14 years. So first we need to know what is the number of half-lives that we have. We'll take the 56 years it's been decaying, divide it by its half-life, which I'm giving units of 14 years per half-life. And we'll see when we do this math out that we have 4 half-lives. So we start off with 28.3 grams. After 1 half-life, we have half of that, or 14.15 grams. After 2 half-lives, we have half of that 14.5, or 7.075 grams. After 3 half-lives, we have half of the 7, or 3.5375 grams. After 4, we're going to have 1.76875 grams. And eventually, and so that's the amount that we're going to have after our 4 half-lives that we've calculated. And we need to round that to give us the appropriate number of significant figures that we need. And golly, I made a mistake, didn't I? Because we have 3 significant figures here. We get 3 here. Let's just fix that right up and make this 1.77 grams. There we go. So it's always important to go back and double check your work. You see, even I often make mistakes. So you'll note that as this goes on, it almost seems like there could be an unlimited number of half-lives because you can always just break this down into smaller and smaller grams. Ultimately, you would get rid of all the radiation. This series does eventually converge to zero, but it is true that it's really slowing down, right? We're releasing a lot of radiation here where we've now in the first half-life released the radiation equivalent of 14-ish grams. And then after the second half-life, we've only released enough radiation for 7 grams and so on. So the amount of radiation being released is going down. And the amount of radiation that's left is going down, but it's slowing and slowing and slowing, and it will take a very long time to get rid of all of the 28.3 grams of radioactive material. And this is really the issue with nuclear waste, is that when it has a long half-life, it will in fact take a very, very long time, on the order of millions of years sometimes, to eventually render it completely safe. Even though it does get quite a bit safer relatively quickly, it does take a very long time to get rid of it all. I want to go over one more example problem where we're kind of working the same thing backwards here. So in this problem, we say after 3 half-lives, 2 grams of carbon-13 remains. So we know how much is left at this point. How much carbon-13 was in the original sample? So here we don't know how much it was in between each one of the half-lives, so we have to work the problem backwards. So if we're left with 2 grams, that means that after the third half-life there was 4 grams. After the second, or before the second, there was 8 grams, and before the first one there was 16 grams. So we started off with 16 grams of carbon-13. I'm not going to show you an example problem for this because it's not really in our homework. But what is interesting is carbon-13 is actually how we go about doing what they call carbon radio dating, where we figure out how old certain things are. And basically what we're doing is we know the half-life of carbon-13. We know how long that takes. We know roughly how much of a sample of carbon-13 there was when something was originally created, because there is like an average number. We saw before it's about 1.1% of all carbon is carbon-13. But once it's trapped inside of an object, like a piece of paper or something, it will begin to decay. And so knowing roughly how much carbon-13 we started off with, and then measuring how much carbon-13 is left in something, and using the half-life, we figure out how old something is. Which is pretty interesting that we're able to do that and track back the age of different items and stuff. And I think that's about it. You guys should now have all the tools you need to be successful in this week's homework.